¿Qué tal? Buenas tardes, bienvenidos a la nueva edición de los coloquios. Bueno, hoy tenemos el gusto de tener a Felix von Oppen, así que cedo la palabra a Lili, que nos va a dar una breve introducción sobre la charla y sobre Felix.
Hola, buenas tardes todos y todas. Voy a cambiar al inglés para presentarla a Felix. Felix introduces himself as someone interested in topological states of matter and their application to topological quantum computation, also strongly correlated and nanoscale electron systems. I think his interests are wider. He works a lot in also, he started doing some work as a PhD student in chaotic systems. He also had very nice works on quantum transport. And we have several collaborations on non-equilibrium quantum systems. So it's, I think, beyond these two topics. And a short biography. He got the PhD degree in Washington University. Afterwards, he holds several research postdoctoral research positions in the Max Planck Institute in Heidelberg, also in Weizmann Institute in Israel, afterwards at University of Cologne, and since 2000 he joined as a professor the Freie University in Berlin. And well, so he visited several times Argentina, Buenos Aires, maybe also Cordoba, I don't think, no. All the times he came previously, he stopped in Buenos Aires, but this time he decided to come back to the south. So I'm very happy to welcome here Felix. And just a very short note, perhaps someone would be interested in asking him questions. Perhaps many of you heard about this story of Microsoft and topological qubits. So I have to say that Felix was one of the theoreticians who inspired this research in this direction, because he proposed one of the first systems, real systems, in which the search for Majorana fermions could be implemented, and I think he inspired plenty of work in that direction, along with other collaborators. So, please, thank you very much.
Okay. I think I should have a microphone. Let me just get the... Okay, Liliana, thanks so much for the kind introduction and for the invitation and hosting me here, and making sure that we had an apartment in the end, and all of that. I should say that somehow South America for me kind of occupied a large part of my imagination as a kid. And Patagonia was one of those places that was occupying me, and I was always hoping to visit, and I thought I'd do it after high school, and I never did, and now I'm finally here. The reason was that my grandparents actually lived, my maternal grandparents, lived in South America at the time, so in Ecuador, in some mountain village, in some development project there, and they had already spent many years, first in Venezuela, and then in Colombia, and then in Ecuador. So anyway, for me, South America was always a kind of a dream place that I wanted to go to, and so many decades later, I finally managed to do that. This place in particular actually also played a role, kind of an initiation as a scientist, if you like. This is something I never confessed, but the first paper that I refereed was a paper by Jagler and Balcero. about something about Aradov-Bohm, and I checked. I think it appeared in PRL, so I may have been very critical, but I think it not entirely critical. So anyway, so that's 2 stories. What I want to tell you about today is kind of a general story. You know, of course, that there's this year we're celebrating 100 years of quantum mechanics, but there's a second, maybe less noticed centennial, which is 100 years of the Ising model. Ising published his paper in 1925 after he finished his PhD studies at the University of Hamburg. He finished actually his PhD already in 1924, which was convenient. I could also give this talk last year, and now I can give it, or some version of this. And one of the things that is quite remarkable about the Ising model is how pervasive it still is throughout condensed matter physics, and in particular also in quantum condensed matter physics and in quantum information theory. And I want to give a few, tell a story that kind of connects the old history of the Ising model to these newer developments. And I'm not, some of you may know this, but some of you may also not be entirely aware of it. So here is the paper that Ernst Ising published in Zeitschrift für Physik in 1925. He was basically interested in understanding ferromagnetism, and he defined so here's the abstract. This is the English translation of the abstract. This is Ising around that time, I suppose. And basically he looks at the thermal behavior of a linear body of a chain of elementary magnets, and in contrast to the Weiss theory of ferromagnetism, which was basically a mean field theory, he wanted to assume that there's no molecular field, but only the mutual effect of neighboring elementary magnets. So in some sense, this was the first time that someone wanted to go beyond mean field theory and actually discuss magnetism microscopically. And unfortunately, he found that the model does not actually have a ferromagnetic transition or ferromagnetic properties, and he claimed, in fact, without any justification whatsoever that is evident from the paper, that this statement, and it's also wrong, that this statement extends to the 3-dimensional model. So that's kind of what he set out. Now, it's entirely impossible to give a talk about everything that came out of this over the decades. It's basically been occupying theorists in particular, but maybe and also experimentalists for the last 100 years. In the first decades, the main question was how to actually, first of all, describe phase transitions in statistical mechanics, and whether the Ising model actually does exhibit a phase transition or not. The first one who argued that there is a transition was Payels. Kramers and Wonnier, under some relatively weak assumptions, actually showed that one can extract the exact transition temperature for the two-dimensional model. And then the question was finally put to rest by Lars Onsager when he solved the 2D Ising model exactly and showed that there was a transition, phase transition in 2 dimensions. The understanding of phase transitions became a lot deeper in the 1960s, when people used the Ising model kind of as a drosophila to study renormalization group methods and the renormalization group theory of critical phenomena. In the 70s, in some sense, the Ising model was then partially taken over by particle theorists. Starting with Wegener's Ising gauge theory, they basically used it as a model system for lattice gauge theories, and actually, as I will tell later, an Argentinian physicist played an important role in this. That was also the time when people looked at spin glasses, basically Ising models with random interactions, and that, of course, is very closely related to neural networks and then to AI as we know today. And finally, in the 2000s, it became clear that the Ising model is actually also very closely related to topological phases of matter, to topological quantum computation, to topological quantum error correction, the toric or the surface code, and then very recently, Floquet time crystals are very closely related and so on. So it's an amazing amount of physics that comes out of this rather trivial model, and I think it's quite a fascinating story. So this talk will in some sense focus on some aspects. I cannot possibly even do justice to this, but on some aspects of this last part. And even that is not enough, because the Ising model actually transcends physics by now. There's still some work on magnetic systems, but for example, there's a paper by Thomas Schelling in the 70s looking at the dynamics of social segregation. Doesn't mention the Ising model, but basically it is kind of Ising-like models. Thomas Schelling won the Nobel Prize for Economy, not necessarily for this work, but at least he's a famous economist. And there's even an Ising model of cancer, whatever that is. I don't know whether this is serious or not, but I thought it was fun that something like that even exists. And this is 2011, so this is pretty current work. Okay, so what did Ising actually do? Well, he simply solved his model exactly. He, instead of using spin up and spin down, he used plus and minus, and basically by enumerating the states of the system, he calculated the partition function and used the partition function to calculate the magnetic moment of the system as a function of the magnetic field, which is this parameter alpha, essentially. Now, this is not the sign in this Gothic letters. It's apparently some old German notation for the hyperbolic sign. So then this may also make more sense. But basically, the upshot of this is that this is at any finite temperature, this is an entirely smooth function, and there is no sign whatsoever of a phase transition in this expression. And that was a nice result, but that was kind of a negative result of the thesis that there's no ferromagnetism in this one-dimensional chain. So this was a bit disappointing, and actually this thesis is in some sense not held in very high regard, and this is kind of maybe put together by Barry Simon, who is a famous mathematical physicist from Caltech, who wrote a book about the statistical mechanics of lattice gases, and in the introduction to the book, or the preface to the book, he wrote this. This model was suggested to Ising by his thesis advisor Lenz. Ising solved the one-dimensional model, and on the basis of the fact that the one-dimensional model had no phase transition, he asserted that there was no phase transition in any dimension. As we shall see, this is false. It is ironic that on the basis of an elementary calculation and erroneous conclusion, Ising's name has become among the most commonly mentioned in the theoretical physics literature. But history has had its revenge. Ising's name, which is correctly pronounced Ising, is almost universally mispronounced Ising. Okay? We'll get back to that, I hope, at the end of the talk. Anyway, so this kind of disappointment apparently was shared by Ising because after he did his PhD in Hamburg, he quit science and worked at the patent office at AEG, at that time a German electric company. But that he also didn't like for very long, and he basically decided to become a teacher, first working at a private boarding school, and later actually taking classes, formal classes for teachers, and became formally a teacher in public schools in the vicinity of Berlin. So that's basically where he went right after. This is him again, and this is with his wife that he married around that time. Now, it is actually very easy to understand why the Ising model doesn't show a phase transition in one dimension. So here is the Ising model in the form as we would write it today. We have spins that can point up or down or take values plus or minus 1. Basically, if the two spins are parallel, you gain an energy J. Let's assume that J is positive, and we only talk about ferromagnets. And if the spins are pointing in opposite direction, there is an energy plus J. associated with it. So there's an energy 2J if you flip a spin, if you break a bond in the model. So on the ground state, obviously, this will want to have all the spins aligned. So you have a ground state of the chain that looks like this. And you can make excitations by flipping one of the spins. But actually, that's not the fundamental excitation of the model. What's actually the excitation are the domain walls that are being introduced, the broken bonds, because we can move this domain wall without changing the energy, right? So we can just flip the next two spins over, and that still has exactly the same energy because they're just two broken bonds along this chain. And it's now very easy to calculate the free energy per domain wall in the system. There's an energy cost associated with each of these domain walls. That's just the energy of the broken bond. We just saw that that was twice the exchange coupling, 2J. And of course, we can place this domain wall anywhere along the chain, and that gives some configurational entropy that is associated with it. The configurational entropy is the log of the number of places where we can put the domain wall, so it's just log of the length of the system, and then times temperature. Now, what you see is that if the system is large enough, at any finite temperature, this is going to be negative, right? And so what that implies is that these domain walls just want to form if you have any finite temperature. And if you have these domain walls in this chain, then you destroy this ordered ground state, and there is no ordered ground state, no ferromagnetic ground state in this model. This is an argument that is famous. It's now usually referred to as the Peierls argument. And in fact, this is the argument that Peierls used in 1936 to show that there is a phase transition in 2 dimensions. He actually did it for 2D. And then you have to have domain walls that are kind of running all the way across the system. Their energy is proportional to the linear dimension of the system. But these domain walls now can also meander around. So it turns out that the entropy of such a domain wall is also linear in the dimension of the system. And now it depends on temperature, whether the energy is larger or the entropy is larger, and whether the system orders or disorders. And Peierls used this to argue that there is actually a phase transition in this system. And then eventually there was Lars Onsager's exact solution, and this actually was hailed by Pauli in a letter to Casimir about World War II physics. Nothing much of interest has happened except for Onsager's exact solution of the 2-dimensional Ising model. So that was kind of the high point of theoretical physics during World War II, according to Wolfgang Pauli. It's also interesting that this is numbered as crystal statistics number 1, so there must be more papers. So the second paper actually is not by Onsager, but it's by Brurier-Kaufmann. And it's 4 years later. This is in 49. This paper is in 44. So they knew already 5 years ahead of time that there would be a sequel to this, or they had so much time that they waited 5 years to write the sequel. And then there's a third paper, also in 49, by Kaufmann and Onsager together. So this is only the first in a series. Brurier-Kaufmann, by the way, was later an assistant to Einstein, so Einstein apparently also liked this work a lot. She was later an assistant to Einstein at Princeton, and then became a professor at Weizmann later past this. Okay, so there was lots of interest in the Ising model, but Ising himself actually didn't know any about this because he had quit physics, but actually far worse than that. In 1933, he was dismissed as a teacher because he was Jewish. And then he became a teacher at a Jewish boarding school in Kaput. I don't know whether any one of you have been to Kaput. It's a small place southwest of Berlin, slightly outside of Potsdam. And in 1937, he actually became the director of the school. And in 1938, after the school was vandalized during Kristallnacht or the November pogroms, and then the school actually had to be closed. Maybe one thing, this is a picture of the school. This is a picture of the classroom. Apparently the school kind of grew enormously in 1933 because not only the teachers were dismissed from the schools, but also the students were thrown out of the Jewish students were thrown out. And so they actually needed an extra space. And this was the extra space that the school rented at the time. Has anyone been there? Recognize it? No? This is the summer house, Einstein's summer house, where he was sailing. So this was right next to the school. So he had a summer house in Kaput, and actually, apparently, they used that as part of the school during some part of these years. Life for Ising then became more complicated. He ran away to Luxembourg. Of course, very closely afterwards, the Germans were taking over, and they actually even annexed Luxembourg. So then he was interned and was still working in part as a teacher in this internment camp, but mostly doing forced labor, dismantling the Maginot Line. And finally, in 1944, he managed to survive as one of a handful of Jews in Luxembourg, and he was liberated by the Allies. And then he could finally emigrate to the US. He actually already had all the papers before the war, except for one, and that's why he had to stay there. So that's what. So because of all of that, he basically didn't know anything about what was happening with his work in the years in between. Okay, so then with this story, let's try to look in a bit more, not really in detail, but just have a look roughly at how Onsager was actually solving the 2D Ising model. He used an idea that Kramers and Wannier had introduced previously, that is to write the partition function of the model in terms of the trace of a power of the transfer matrix. Now, probably most of you have done this exercise when you did your statistical mechanics class to solve the 1D Ising model using the transfer matrix. In 1D, n is just the number of sides of the chain, and T is just a simple 2x2 matrix. But in 2D, you're actually adding rows with every power. So the power here is just the number of these rows, and this is a drawing from Onsager's paper. And the dimension of the matrix is now 2 to the n by 2 to the n, so n being the number of sides around this ring. And then you can write it in terms of Pauli matrices, where x and z are just Pauli matrices, sigma x and sigma z, but that's just for short here. And it turns out that the transfer matrix takes this form, where there's one term that only acts on all of the spins separately, and there's one term that acts on neighboring spins. And this is now basically a quantum problem because it's written in terms of quantum spins and the Pauli x and Pauli z operators. Now, actually, you can simplify this a little bit. If kx and ky were very small, then you could combine these exponentials. Otherwise, this matrix multiplication, you have to be careful. But if kx and ky were small, then you don't make much of a mistake by just combining these exponents. And that's something that was done by a famous Argentinian physicist in his PhD thesis. Here he is, Eduardo Fredkin. So he basically, the exponent then you can interpret as a Hamiltonian, and that's the birth of the quantum Ising model, if you like. That's what it's called, or transverse field Ising model. It has an exchange coupling between neighboring sites from one of these exponential factors, and it has, which tries to align the spins along the z direction, and it has a magnetic field in the x direction that is trying to align all the spins into the positive x direction. And of course, depending on j and g, they either will align along the z direction or mostly align along the x direction, and that is the competition that is described by this quantum Ising model. And this is what is really pervading all kinds of places in quantum condensed matter physics now. This quantum Ising model, is basically the drosophila for symmetry-breaking quantum phase transitions in this spin representation. We will see that you can also write it in terms of fermions. If you write it in terms of fermions, it becomes the paradigmatic model for topological quantum phase transition, and you can find Majorana zero modes in this model. If you go to a dual description in terms of these domain walls, and in particular, if you do this in 2 dimensions, then you end up with a lattice gauge theory, which is basically what's being done or used in topological quantum error correction, surface code or toric code. And finally, if you go to a Floquet version, which we'll also discuss in more detail later, this gives rise to Majorana pi modes and time crystals and all kinds of things that have been discussed in the last few years. So that's basically where what I want to discuss, mostly this and this a little bit in the rest of the talk. So let me maybe check quickly how I'm already way over time. Okay. So the first part is, here's a article from an Argentinian newspaper that I'll explain to you some background of. This is about the Microsoft story that Liliana already mentioned at the beginning. And then I might say a little bit about the experiment by Google that this one starts from the Hamiltonian version. This actually starts from this version of the transfer matrix in some sense. Okay, so here's the quantum Ising model, and let's think a little bit more about the physics. So here's again the Hamiltonian exchange coupling, transverse field. One of the fundamental properties of this Hamiltonian is that it has a spin flip symmetry. If we flip all the z's to minus z's by rotating by 180 degrees about the x-axis, then x remains the same, z times z also remains the same because you get 2 minus signs. So there is the spin flip symmetry that is the fundamental symmetry of this model. The phases or the behavior of the model we can rather easily understand by just taking the limits. If this transverse field G is much, much larger than the exchange coupling, let's set the exchange coupling to 0 for a second, then all this Hamiltonian wants to do is to just have all the spins aligned along the positive x-axis. Very boring. There's just a single ground state. All the spins are aligned along the positive x-axis. If, on the other hand, we set J finite and G 0, so J is much larger than G, then all we want to do is to align the spin along the z direction. And so you either have a ground state in which all the spins are spin up along the z direction, and we could, of course, equivalently have a ground state in which all the states are aligned along the spin down direction and the z direction. Both of them have exactly the same energy because they don't have any domain walls in them. And so there's a transition happening because this is a single ground state and this is a degenerate ground state, and you cannot have both at the same time. You have either one or the other, so there needs to be a phase transition in between. And it turns out that this phase transition happens exactly when G is equal to J. This is, as I said, the drosophila for a quantum phase transition, transition in the ground state of the nature of the ground state in the model. The ferromagnetic side has a broken symmetry associated with it, whereas the paramagnetic side, as usual, has is symmetric, symmetric state. So this model has this 0 temperature phase transition, quantum phase transition. And in fact, this is simple, but we can actually solve it exactly. I already alluded to that there is a transformation to fermions that solves it exactly. So the basic idea is just that spins can be either up or down or right or left, whatever, whichever quantization axis you want to use. And fermions, if you have an orbital, they can either leave it empty, or they can occupy it once. There's no 2 fermions in the same orbital, right? So there is 0 and 1. So that looks the same. There's a bit of a difference because spins at different sites will commute and fermions anti-commute, but there is a way of technically fixing this, which is called Jordan-Wigner transformation. Basically, you can map the spin operators z and x to something that is fermion creation and annihilation operators, and these string operators take care of the fact, don't worry what they are, they take care of the fact that these commutation relations work out the way they're supposed to. If you should be interested in learning about this, then there is a good, nice old book by Lieb and Mattes from 1966 that has all of this, and it was actually reviewed in Physics Today at the time by Freeman Dyson under the title Trip to a Beautiful World. And it's kind of fun to look at the illustration for this article, which is here. A trip to the beautiful world of one dimension will refresh his, at that time there were only male physicists, no female physicists, will refresh his imagination better than a dose of LSD. That was published in Physics Today, and here's the LSD, here's the line, the one-dimensional. Anyway, so I thought that was kind of cute. I don't think you would see it in a physics journal these days. Okay, and so if you do this mapping, then you map this quantum Ising model to a fermion model, which is now known as the Kitaev chain. And instead of showing you the details, let me try to convince you how this mapping can work. This is basically just a superconductor model. It has pairing terms, it has hopping terms, and it has some energies for creating these fermions. So it's just a mean field Hamiltonian of a superconductor. So how the hell do you get from this spin model to a superconductor? To maybe try to understand that, let's think about excitations away from the ground state in the paramagnetic phase. So all the spins in the ground state, they all want to be aligned along the positive x direction, but there's one excitation in the system. We can also put more excitations. They're all ground states in the limit of J to 0. Now, what J does, it basically flips two neighboring spins along the x direction. It flips them. If it's like this, it flips the neighboring spins like this, or if they previously looked like this, they've now flipped like this. Z just flips states that are polarized in the x direction. So now two things can happen. The ZZ term can either, if it flips these two spins, then now this one is flipped in the wrong direction and this one is flipped back to the right direction. So basically you've moved this excitation. And this excitation, by the way, of course, is the fermion. It's also fermionic. You cannot put two of these spin flips on the same side. It's impossible. There's only one. There's no spin flip or there is one spin flip. So this is kind of like a fermion. And you can hop these fermions, or you can act with the two neighboring Z's on two spins that were not flipped at all before, and now both of them are flipped in the wrong direction. So you basically introduce two fermions on neighboring sides. Okay? So this is like the pairing term in the Hamiltonian. You flip two on neighboring sides, and this is like the hopping term of the fermions. You take the fermion to the spin flip to the neighboring side, and of course every time you flip a spin, it costs you some energy. So this is the origin of this 2G term. Okay? So this is how you get from a spin model to a superconductor. It's kind of amazing. And it was first solved exactly by Ferti in 1970. So as I said, this is known as the Kitaev chain. And one question that you now want to ask is, what is actually this phase transition in the spin system in the fermion system? Naively, you might think, well, maybe it's a superconducting transition. It goes from normal to superconductor. But actually, the prefactor of this pairing term is J, and J doesn't change where you are here. They're all superconducting. Anything along the line has the superconducting pairing. So it's not a superconducting transition. Now, I find it amazing. This was done in 1970, and for 30-some years, until Kitaev, no one apparently asked the simple question, what does this phase transition mean in the fermionic description of the model? Whoever would have asked himself or herself that simple question would have discovered topological phases of matter. It was just lying there on the street, so to speak, and lots of very intelligent theorists have looked at it in the meantime, but no one apparently asked that question. Anyway, so what it does is it becomes a topological phase transition between a trivial superconductor, which is analogous to the paramagnetic phase, and a topological superconductor, which is the analogon of the paramagnetic phase on the spin side. And the spin flip symmetry of the Ising model becomes a fermion parity symmetry of the Kitaev chain. Basically, a symmetry that there's even and odd, that the fact that even and odd fermion number are conserved. This can only add fermions in pairs or leave the number of fermions conserved. So if you start with an even number, you will always have an even number. If you start with an odd number, you'll always have an odd number. So that's how it works. And so there's very interesting physics here on the fermion side that was kind of ignored for a long time. Now this is actually where we can now connect to the Microsoft story and this newspaper article. I don't want to go into any details, but I can explain to you maybe why this makes possibly a good qubit if you're on the fermionic side, if you go to the Kitaev chain. If you look at the quantum Ising model, we had these two ground states, all the spins up or all the spins down. And at the lowest level, they have the same energy. If you actually turn on G, then there's a small splitting, because in Lth order perturbation theory, if L is the number of spins in your chain, you can flip all of the spins, and you can have a small matrix element that connects these two states. But this coupling is exponentially small in the number of sides of the chain. So it's a very small splitting. And it turns out that this happens throughout the entire ferromagnetic phase. Now this is a nice degeneracy, but it's easily broken because it's only protected by this Ising symmetry. If I add a term to the Hamiltonian that breaks this Ising symmetry, for example, a term that just puts a magnetic field in the z direction, then of course these two states will immediately split in energy. One will get a higher energy, the other one get a lower energy. And since in an experiment there will always be a little bit of a magnetic field in the z direction, this degeneracy will not be very useful to do something computational with. But if you now do the same thing in the Kitaev chain, you should have the exact same degeneracy on the fermionic side, because you're just mapping one model to the other. And in fact, the entire spectrum of the Kitaev chain falls apart into a set of even levels, even fermion parity, and a set of odd levels. And there's just an exponentially small splitting between these. On top of it, it's a superconductor, so the ground state is protected by a gap from the excited states of the model. And so what Microsoft basically wants to do is to use this degenerate set of levels to build a qubit. It's slightly more complicated, but not much more complicated than that. Now, you would have, of course, the same kind of perturbations, but if you look at it, the z term, we looked previously how it looks in terms of fermions. The z term in terms of fermions is c plus c dagger times something. This has an odd number of fermion operators in it. Okay? That this is an even number. So this is just changing the fermion number from even to odd, or from odd to even. But that's just not allowed in physics. Yeah, there's something called fermion parity, super selection. You just cannot write a fermion Hamiltonian that has an odd number of fermion operators in it. It just doesn't exist. Okay? So what would destroy the degeneracy here will never destroy the degeneracy here, because it just doesn't exist. Okay? So this degeneracy is much more protected than the degeneracy on the spin side. And that's because of the topology, and this makes this potentially a very useful qubit, very, very hard to realize, but maybe useful, whereas this would not make a very good qubit, or at least no better than any of the other qubits that we have. So that's the basic observation for what Microsoft wants to use for their qubits. And it's basically impossible to make this split away from each other without closing the gap to the excited states, without closing the superconducting gap. That's what makes this so protected. And in a different language, that this would be associated with the fact that there are Majorana zero modes sitting at the ends of these fermionic chains. Okay? But coming from the Ising model, you can also understand this in a different way. Good. That's this Majorana 1 chip that Microsoft was announcing sometime just a few weeks ago. That was where this newspaper article came out in February of this year. And Chetan Nayak wrote in a Microsoft blog, which you find easily by Googling it, it says, a hardware-protected topological qubit. Research published today in Nature, along with data shared at the Station Q meeting, demonstrate our ability to harness a new type of material and engineer a radically different type of qubit that is fast, that is small, fast, and digitally controlled. That's basically the qubit that I discussed on the previous slide. Now you have to still find a way of realizing these kinds of Kitaev chains. They were fermions, they didn't have spin. It was actually a p-wave superconductor. That's a story that many of you know as well as I do. So the idea and what Microsoft is pursuing is to use semiconductor wires that are covered by a thin layer of superconductor. The semiconductors are indium arsenide. The superconductors are aluminum. And if you put this into a magnetic field, there is some chance that this will realize this topological superconducting state of the Kitaev chain. And the real qubit then would consist of two such wires that are coupled. I made a mistake. I wanted to turn it off before. And no, it's a. Let me actually be sure that I really turn this off. Okay. So it consists of these two wires and a ordinary superconducting bridge. It has these Majorana zero modes at the end, and then there are things to measure them. And that's basically what Microsoft claims to have realized. There are no data published that really show this. This Nature paper only discusses readout of a single wire, and it doesn't really prove that they are Majoranas. But the claims are quite strong, and it will be interesting to see in the next few months or years how far they really got with this. Recently, we've been writing a bunch of reviews on this, if anyone is interested. Okay, but that's roughly where I want to leave it, a basic idea, but there's lots more to tell, but that's not the story of today. So let me use the remaining time, if there's any. Still a little bit. On a second story, which is related to an experiment that was done by Google Quantum on their chip. And this really connects directly to the transfer matrix in this form. So here again is the transfer matrix, but this kind of looks like these kind of look like time evolution operators in quantum mechanics, right? Except that the Ks are real. So let's make a Wick rotation as we do say in theory, and just make this, add a factor of I here. So we basically make these prefactors imaginary rather than real. Then these are real time evolution operators. And these are time evolution operators of the kind that you can directly implement on a quantum computer, because all this does is to take a single qubit, which is just a spin, it's just a two-level system, and rotate it by some angle about some axis. This is exactly what a quantum computer is supposed to be able to do. And this is just to make a two-qubit gate, a joint rotation of two neighboring qubits. Again, something that is exactly what a quantum computer should be designed to do. So after this I, we realized that this is actually a unitary a time evolution operator in quantum mechanics that can be directly implemented on a quantum computer, and this is basically what Google did on their chip. So basically, if you want to do this, you can, for example, take your quantum Ising Hamiltonian and turn on, say, the transverse field for a while, leaving the exchange coupling off, right? If depending on how strong this coupling is and how long you leave it on, you rotate by different angles. So this is basically directly implementing this thing. K is just the strength of the coupling times the time over which you leave this coupling on. Then stroboscopically, you switch the the transverse field off and turn the exchange coupling on. And so then you do this, and again, this prefactor is just the coupling strength times the time that you leave the coupling on. And then in this Floquet business, you just keep repeating this, okay? So you apply this operator, this time evolution operator, t times to your whatever initial state you have, and you can represent this as a quantum circuit where these q's are just a sequence of qubits, or equivalently spins. And first you apply these x rotations, single qubit gates to this chain. These are all of these operators. There's a sum over j, so you have to do this for every single spin along the chain. And then you do these 2 qubit gates to all the neighboring spins. So you first do the even pairs, and then you do the odd pairs. But this is then implementing this, okay? And then, okay, you can also in principle do more, but then you repeat this for t cycles. And then in the end, you read out your qubits or you read out your spins and measure something and study what you see. That's basically what Google was doing. And in fact, they did a bit more, as I said. So here's the initial state. This is what they do. Apply this Floquet operator t times. And then this is the final state on which you can do measurements. They not only had the transverse field and the exchange coupling, but they also put a field along the z direction, which was actually random along the chain. It was the same field in every period, but it was random along the chain. Okay? And again, these are both are single qubit gates, and this is a 2 qubit gate. And that's what they know how to do. And what was surprising was that even with this longitudinal field, with all this randomness, they found that the bound, so this is basically all the spins from, these are 40-some qubits. This is the time, and at every time they measured whether the spin, so they ran it for a certain time, and then they measured whether the spin was up or down, okay? And then they averaged. And they found that on the edge, it was up, down, up, down, up, down, up, down for hundreds, t equal to up to t equal to 200. Basically, it stopped because the qubit died. The qubit has a certain correlation time, and at one point, it doesn't stop. Turning on the randomness didn't do much to these oscillations. In the center of the chain, it dies out very quickly. And they can also do it in a different parameter regime out here, where it just remains constant along the edge. And again, in the center of the chain, it dies very quickly. And it's kind of remarkable that these boundary correlations persist for such a long time. Because if you turn on this longitudinal field, you break the integrability of the model. You cannot solve this exactly any longer. You need to use a computer to solve it. You break the spin flip symmetry of the model. So also you break all the symmetries. And actually, in many ways, this is a correlation function at infinite temperature. So nevertheless, these spin correlations seem to exist for a very long time. And I thought was crazy, and I wanted to understand better, and that's what I want to tell you a bit about in the last few minutes. The first thing to realize is that if you deal with a Floquet system, there's no ground state any longer, okay? Because we can now only diagonalize this Floquet operator, and this is a unitary operator, so it has a unit modulus eigenphase. And so these ENs, which are kind of the eigenenergies, they are now just defined on a circle from 0 to 2 pi, and you start over again. There's no lowest energy in this. It's just like in a solid, k goes from minus pi to pi, and then you start over again. Here, energy goes from 0 to pi, or from 0 to 2 pi, or from minus pi to pi, and then you start over again. There is a Floquet period of 2 pi in the energy. But if we understand this, we can now understand the phase diagram of the clean case, so no longitudinal field to start with. Actually, this has a richer phase diagram than the Hamiltonian model, because now the Floquet period gives you another energy scale. So previously, only the ratio between exchange coupling and transverse field was an important parameter. But now you have a third energy scale with which you can measure both J and G. So G and J are both independent coupling constants of the model. And it turns out that there are 4 phases in this. 2 of them are basically the analog of what we had before. And so in this trivial phase, this is the trivial superconductor, if you like, or the paramagnetic phase, all of the eigenphases are non-degenerate, and they're somehow distributed around the unit circle. But if you're here in this Majorana zero-mode phase, or ferromagnetic phase, then all the phases come in doublets. This is the analog of this thing for the Hamiltonian model, that all the states came in degenerate pairs. But here, one more thing can happen, and that is in this phase that the eigenstates again come in pairs, but they come in pairs that differ by pi. Okay, so any state here has a partner on the other side, and any state here has a partner on the other side here, and so on. Okay, so they're all pi paired. And this happens up here. Finally, in this phase, both of the things happen at the same time, so you have both this and this at the same time. Now, why does this happen? Let me just give you a hint of that. If you go here to G equal to 1, okay, and look at this operator at G equal to 1, it actually is just the product of all the X operators. This is an operator that just flips all the spins from being spin up in the Z direction to being spin down in the Z direction. Okay? So this kind of gives you something that if you start out with up, next period you're down, next period you're up again, down, up. So every time you get a minus sign with every period. And that basically, these pi pairs is a reflection of this fact that it kind of flips and you only get back every other time. Okay? So that's why this phase exists as well. And this now kind of explains this. If you're in this phase, all the levels are degenerate or almost degenerate. So energy differences are there are many energy differences which are 0, and you kind of get a constant, at least on the edge. We can discuss later why it's on the edge. And in this case, you have this pi, and so there's many pi differences, which gives you +1, -1, +1, -1, and that's why on the edge in the clean system you get +1, -1, +1, -1, +1, -1. You get these oscillations, these alternations in the sign of the spin with every cycle of the Floquet operator. Okay? This is actually directly related to the Majoranas, and these are now real Majoranas. Well, they're not real Majoranas because it's not fermions, but you Fourier transform these curves basically on the edge, and this is what you find. And for those of you who know, this is G. So this is from 0.5 to 0.8. So we're going up along this line. We're in the pi phase, and omega over pi equal to 1. There's a strong peak, which is the pi Majorana in this story. If you go close to the phase transition, they split, as you would expect from Majoranas close to a phase transition. If you're in the zero mode phase down here, at 0.5, they again start to split, but otherwise there's a strong peak at 0, frequency equal to 0, which is just the 0 Majorana. And more generally, there are all these other states. This is just the Bougulier of the Gen spectrum of the superconductor. Okay, it's nicely symmetric, positive energies, negative energies, positive energies, negative energies. And you see how they change as a function of the coupling constant. This is the direct measurement of the Bougulier of the Gen spectrum on a quantum computer. Okay, or a simulation of the Bougulier of the Gen spectrum on a quantum computer. It's quite nice. It's almost, I think, order of magnitude 1,000 gate operations. You Fourier transform the data, and it does what it's supposed to do. I actually didn't expect that they're as good as this, but I was amazed that this worked. Okay, it's not really a Majorana, as I said, because it's all spins and not fermions, but still, it's kind of nice to see this. So again, but these measurements were actually done in the presence of this longitudinal field. And again, it breaks spin flip symmetry, breaks integrability. So how can that be so stable? We already said that if in the spin system you apply a magnetic field along the z direction, it immediately splits the degeneracies. Okay? And yet the constant stays, and the same in the pi mode. So it was kind of surprising. And in fact, if you do the calculation and just diagonalize this numerically and calculate these eigenvalues of the Floquet operator, and you look at these splittings, and you do that first in the Majorana zero mode phase, where they should all be degenerate, and you just make a histogram of these splittings throughout the phase. Okay? And you do this for different strengths of this longitudinal field. If the longitudinal field is 0, then let's say let's normalize these splittings to -1 and +1. But if you turn on the longitudinal field, they immediately split. So the distribution function, they widen, right? So all the splittings get larger. None of the splittings get smaller. It stays 0 in between the bare splittings. This is what you expect. This is just what I explained before. Longitudinal fields break the symmetry, split the degeneracy right away. And in fact, this happens for fields that are as weak as 10 to the -9. Okay? So the extremely small fields immediately split these levels. Yet the correlation function remains constant. If you look at the pi pairing, it's just the exact opposite what happens. If you do the same thing, here is -1 and 1, and you turn on the random field, all the splittings become smaller. There's not a single splitting that becomes larger. They come closer to pi. Okay? Here, again, we are just looking at how close they are to pi and plot the histogram of how far they are away from pi. And if you make the random field very strong, 0.2, this is 8 orders of magnitudes larger than this. They're all still smaller. Okay? And so this pi pairing and this alternation seems to be getting better as I turn on this random field. Actually, again, 8 orders of magnitudes different, strengthened in one case, split rapidly in the other. Why? Actually, it's a very simple thing. You just need quantum mechanics perturbation theory in order to understand that, slightly modified. We are now adding another factor to an unperturbed unitary operator, okay? And we want to now look at how the eigenphases change if we turn on a weak perturbation V. Okay? So you do the calculation, or your student does the calculation, and you find that the first order shift is just the expectation value of the perturbation of the unperturbed states, which is what we all know. And in the second order, it looks a little bit different, but it's also the same. It's a sum over all the other levels, matrix elements squared, divided by, okay, now we have to be careful because the energies are actually periodic, so there should be some trigonometric function, and it turns out to be the tangent of the energy difference divided by 2, and there's another factor of 1/2, so that if these energies are very small, then all the 2's cancel, and you can expand the tangent, everything cancels out, and you get back to ordinary quantum mechanical perturbation theory. Okay? Now this is all you need, and actually you can even do away with it and just look at the pictures. If we are having 2 degenerate levels and we perturb them, they will split because there will be level repulsion due to the perturbation. If they are at pi, then they also try to split or get repelled from each other, but they get repelled this way around the unit circle, and they get repelled that way around the unit circle. And this repulsion is a bit stronger because they're closer along this direction than along this direction. So they actually push to pi. Pi is the stable point. If you turn on the perturbation, you push them towards pi. 0 is unstable, but pi is a stable point in the story. And so you actually have an attraction to pi and a repulsion from 0, if you like. And that's the fundamental difference between the 0 modes, where you have all the levels being degenerate, and the pi modes, where you have all the levels being different by pi. And actually, you can make this distribution function, I should look again. I should get done. I'm also quote. You can do this self-consistently, and you can actually reproduce these curves just by using a self-consistent version of this perturbation theory. So this is really what's going on there. Now, why would you care? Well, the Fourier transform of the spin correlation function, which is what we are plotting here, is basically just these splitting distributions of these levels. Okay, so understanding these splitting distributions basically tells you how the spin correlation function looks as a function of time. And in fact, what this tells you is that what Google observed was really just the beginning of things. In principle, applying a longitudinal magnetic field does not only preserve the correlation function, but it actually makes it persist for longer and longer times, which is just a fun fact. Now, you may not care much about this, but one thing you can do is you can apply the same logic to Floquet time crystals, and you look at the splitting distributions, and it turns out that they are perfectly log normal, and so you can fit the correlation function of these time crystals, or basically have an analytical expression for the correlation function of these Floquet time crystals that is just the Fourier transform of a log normal splitting distribution. So you can apply the same logic here. And, well, this I will simply split. Let me close this so Liliana can relax, and I'm done, by telling you how Ising's life continued, and to come back to what Barry Simon was saying. Well, he became a professor of physics in a teaching college, so not really doing research, but just teaching. It was a place called Bradley University in Illinois. And in 1953, he became a naturalized US citizen, and actually in that process, they changed the name to Ernst, from Ernst to Ernst, or from Ernst Ising, presumably to Ernst Ising, and from Johanna Ising to Jane Ising. So actually Barry Simon, I think, was not right. Saying Ising is just as correct as saying Ising. You can do whatever you like. Ising actually lived quite long until his 98th birthday, but that's nothing compared to his wife, who passed away on her 110th birthday. And I'm sure that the model is actually going to continue living well beyond 110. And with that, I think I'm done with the talk. I think I should still acknowledge the PhD students that did the work that I was talking about in the end, Harald Schmid and Alex Penner, and the postdoc Kang Yang, a former PhD student, now a professor in California, Yang Peng, and well, actually I didn't talk about this, but Leonid Glasman and Gil Rafael were also very much involved in this story. And with that, I'm done, and thank you for your attention.
Some questions.
Well, first of all, thank you for the talk. It was really nice, interesting. I have a question, maybe it's rather technical, but you perform a sort of Floquet stroboscopic analysis.
Absolutely.
So this is valid period by period, no? So what's going on in the middle? Because you compute the correlations for any time, or also you compute the correlation stroboscopically?
Well, so in some sense, we are doing simply what Google is doing, which is to apply these gates, and we don't look at what's happening inside of the gate operation. We only look after the gates are complete for a cycle. And just numerically, it's a lot easier to multiply matrices with each other, which is what you do to multiply these time evolution operators, than to actually take a Hamiltonian that is time-dependent, exponentiate it, you have to, and trotterize it, you have to look at a much finer time scale. It just makes your numerical work much harder. So we are really just taking the unitary operator as I wrote it and multiplied it as a whole. So time only took on discrete values. There was t equal 1, t equal 2, t equal 3, and so on and so forth. No, nothing in between. Okay, but that's what Google also does. They just apply their gates, and then they look at, after doing this 5 times, 10 times, 100 times, whatever. It's just numerically a lot more convenient.
Any other question? Yeah.
Hi, thank you very much for your talk. It was really interesting. I wanted to ask you, in this Floquet evolution that you see stroboscopically and measure the Majorana zero modes and pi modes. Thus, the transformation to fermions, if you remove the Z field that breaks everything,
Yeah.
does it still work? And do these modes that you see are actually Majorana modes after transforming?
No. So you can solve these Floquet operators. You can diagonalize them just by the same tricks. Jordan-Wigner works just the same as for the Hamiltonian. And of course, yes, you find also these Majorana modes in zero modes or pi modes in the process. Again, I think maybe, so Majoranas in a spin system are something else from Majoranas in a fermion system because of what I was describing, that in one case it's protected by symmetry and they are simple operators that are very physical that immediately destroy it. And on the fermion side, there are no operators that kind of destroy it, and there's some topological protection associated with it. So yes, it's formally, in terms of the solution, it's Majorana zero and pi modes, but in the really physically interesting Majoranas are the ones that you have in truly fermionic systems, not the ones that you simulate in a spin system. Okay. So.
Any other question? Okay, we don't see any other questions. So let's thank Felix again. Thank you.
Thank you.